Do you hear me all right? Okay, thank you. Welcome everyone. Thanks for joining me this early morning after the big JFocus party. I know it must be hard. I'm here to talk about serverless. I suppose that most people here are familiar with serverless, at least heard the term, and perhaps even played with it. You know, Amazon Lambda and OpenWhisk and other things. But I'm going to try to look into the future and see a little bit what we hope to expect from future serverless and what I think serverless should be in the future. And not just talk, but actually showing you a reality that we've been working on from Lightbend's side on this. Also partnering up with some other companies. So just get started. By the way, I'm Jonas. If you don't know that, Jonas Bonér. I'm the CTO and co-founder of Lightbend. Started the AKA project, and yeah, so you have a little context where I'm coming from when I'm rambling. So there was a recent, or it was about a year ago, a positioning paper by Berkeley Computer Science Department that came out, so looking into the future as they do every 10 years. They did the same thing with cloud computing. Writing this positioning paper. And one of the conclusions here from this paper was that they say, and I quote, "We predict that serverless computing will grow to dominate the future of cloud computing." And I think they are true. That's true, you know. And I think the way they look at it and the way I look at it is that, you know, serverless is all about a new experience, how we develop, sort of deploy, operate, you know, manage software in the cloud in general. And that experience is here to stay. You know, and the whole thing about that experience is to sort of outsource as much as absolutely possible to the runtime and to the service that you guys are using, so you can focus on the business logic. You know, story repeats itself. You know, that we've heard that, you know, over and over the last 20 years. But I think we're getting a little bit closer to the dream every sort of time around. How many here have heard about function as a service? It's like everyone, almost. That's great. I really think that function as a service is really truly visionary. It's sort of what was started this whole serverless movement, or kicked it off and shown what was possible. You know, it's really sort of paved the way. But I also think that it's just the first step. It's the first step on a long journey towards, you know, this nirvana of computing. And I really think that it's not equal to serverless. A lot of people, when they say serverless or think serverless, they think function as a service. And I think that sort of cuts it, that sells it really, really short. Function as a service is a great first incarnation, first implementation of this new serverless experience. But I think that's all there is to it. You know, it's the first step. Let's build it upon that and see where we end up. Yeah. So, but before, you know, I start to talk about why I think it's too limiting. Let's talk about first, you know, what is it good for? What is function as a service good for? Why you do? When can you use it and need it? You know, and you know, in general, I think it's great where use cases are where throughput is really key. You know, rather than low latency. And where you have sort of a type of use case where requests can be completed in a fairly short amount of time. And I won't go through all of these in details. This is not an exhaustive list either, you know, but you know, some of the things that are great is like parallel processing, you know, processing-centric things. Things like, you know, classic examples are image processing, object recognition, and all these things, you know. And it's great for a lot of other things, orchestrating functions, you know, sort of workflow type of things where you pass data through, you know, usually doing some annotations or processing or merging and splitting on the way. But the thing is that with function as a service, it's really hard to build general purpose applications. It's usually that you end up with a subset of your full app, at least if it's a non-trivial application, where function as a service is great. And you wish you could put your whole app in Lambda or something, but it's just this use case, you know. So you end up with something like a hybrid, or you try to shoehorn your whole system into Lambda or whatever function service sort of system you're using, and you suffer from the consequences of it not being ideal for the rest of your application, just this use case, you know. So some of the problems with and the reasons why I believe that it's not well suited as a general purpose sort of backend for any type of application is that first functions are stateless, ephemeral, and short-lived. They're getting killed after a certain amount of time, all in the name of efficiency and sort of both energy and cost efficiency, which is great, of course. But it's actually quite expensive to always lose this computational context for a certain type of applications. If it's processing-centric, just passing data down the pipeline, it's fine. But if you're not, it can be very tedious to always have to rehydrate your state back. And the other problem is durable state if you need it. You can use Dynamo in Lambda, for example, but it's always somewhere else. So whenever you need it, you always need to fetch it. And whenever you want to, you make sure that it's actually, persisted. You always need to persist it somewhere else. So there's always a network hop. There's always somewhere else, and this somewhere else, we've sort of been used to that with classic 3-tier architectures and CRUD applications, and Lambda is really, or functions as a service, I would say, is really nothing different. It's like this classic 3-tier stateless architecture, which again serves this certain type of use case as well, but others not. Another problem is that there's really no co-location of state and processing. It's the most efficient way you can operate a state is, of course, to have it right where you want to use it. And since you constantly lose that locality reference, that's also a problem. Another is like there's no direct addressability. You always have to communicate over some sort of durable medium. PubSub is great. It absolutely fits a ton of use cases, but it's sometimes very inconvenient to always have to communicate and coordinate over. I mean, the guy you're actually communicating with and want to coordinate might even sit on the same node, on the same Kubernetes pod, right? But you still have to always go through some sort of PubSub medium. So having a way of directly communicating point to point could be useful. There's also limited options for managing, coordinating distributed state in general, and consistency guarantees is like one size fits all. So the question is, what is the missing piece? It's a thought through sound way of managing state, I believe. So the elephant in the room here is the state. This is what we constantly keep ignoring, and I think it worked better 10 years ago than it does today, because nowadays a lot of our apps are centered around data, and a lot of our use cases are real time, that our users demand us to give answers to insights into data, in close to real time. And the data sets gets larger and larger and larger, which also makes it hard. So a lot of our apps are actually evolving around state, and I think we should get serious about state and actually incorporate into the model better. Make sense? Okay. So what I think that we need. Sorry, this was. This was the wrong order of the animation. This should be the last one. So I'm just gonna remove this. Sorry, I don't know how that ended up. Let's move this one out. So we need. I would like to have serverless support. I mean, this serverless experience I'm talking about, having that for applications like, for example, managing in-memory durable state across individual requests, like classic things like that fits that use cases, like user session, shopping carts, caching, things like this. Things like that. Low latency serving or dynamic in-memory model, something that's huge in machine learning and AI and these type of things. That's really hard if your data is always somewhere else. You need to build up this model in memory and have it persisted in memory, so you don't lose all the value you've been aggregating over time, building up this model. Real-time stream processing, things like recommendation, anomaly detection, distributed resilient transactional workflows, without having to always checkpoint down into a database. The Saga pattern, the workflow orchestration, shared collaborative workspaces, all this, also classic things like, in distributed systems, hard distributed systems problems, like leader election counting is actually really, really hard, voting and things like that. I mean, you might say, sure, I can do all of that in Lambda and functions as a service. Absolutely. I mean, it's Turing complete, You can do all this in almost any Turing complete, you can do this in any Turing complete sort of system. But it's really hard to do it efficiently, especially since a lot of our apps now revolve around data. Okay? So what are the technical requirements, I think, in order to actually get this done in an efficient way? We need support for stateful, long-lived, addressable virtual components, meaning that they can be activated and passivated in an efficient way. Actors fit this bill very well. Of course, I'm biased, I love actors, but I believe that is truly something, their model that can encapsulate this very well. It's also the reason why a lot of serverless frameworks are actually built around actors. OpenWhisk is even built on Akka, even though it doesn't use its state model that well. So I think it's time to bring in the state side of actors, which is actually the thing that they do best, I believe. Other things is like options for distributed coordination and communication patterns beyond pub/sub. We have pub/sub, of course, but we want point-to-point, we want broadcast, we want ways of managing coordinate state instead of without always going down to a database. Do it right, peer-to-peer. And this is like classic things we've solved for ages, in distributed systems, but we just need to bring them back. Options for managing distributed state reliably at scale in general. And I think we need ways to do that range from strong consistency that you have in key value store most of the cases, or actually probably at least SQL databases. A lot of key value stores are eventually consistent, right? So you want the whole range from strong to eventual consistency through causal consistency, and because a lot of things revolve now around workflow, and A did something to B, and tracking that causal relationship is sometimes all you need. You don't need strong consistency, which is even more, even less efficient, and sometimes not what you want. Essentially, I want like consistency a la carte. So having a way of picking the right consistency guarantees for my problem, because the more guarantees you have, the less headroom you have for scale, and the harder it is to make available, etc., etc. Right? And intelligent placement of functions as well. If I know that my state is over there on that node, I don't want to run it here. I want my runtime to figure that out and put my function there where my state is, or vice versa, right? It's often easier to put the function where the state is because it's less things to move around. And this means, bringing in things like sharding, sticky routing, and things like this. Predictable performance and latency, of course, is also part of it, as well as managing end-to-end guarantees, which is actually quite hard if the only thing you have is a function that you can sort of test and give, make sure that it lives up to certain properties. But what happens when you stitch them together? Do they preserve the same guarantees? And having more high-level ways of thinking about composing these building blocks in a way that makes sure that you actually can ensure end-to-end guarantees, correctness, consistency, safety, all these things. Okay. So functions as a service, it's great at abstracting over communication. So you have this box, the user function, and you message in. You don't need to care how it ended up there. It just ended up in your mailbox or in your queue, and you have a message out. Okay, so that's very easy. But when you bring in CRUD, I mean a practical example. For example, if you use Lambda and you have Amazon Lambda, I'm talking about now, and you use DynamoDB, for example. If you use that, then the problem, I believe, that that's really not serverless in the ideal sense. And let me elaborate a little bit on that, because it's really a leaky abstraction. Because the thing is that if you're managing the database from within your function, then you're bringing in all the complexities of data management, of querying, of actually doing the persisting, the commit, and everything into the function. So the function needs to do all the work of managing and persisting data and making sure that it's it's used the way it should do. And the problem here is that that's essentially sort of a black box to the runtime. When the runtime wants to look into, see if I can optimize these things, then it really can't do much, because it just sees this opaque function with all this data management going on inside. Okay, so the big problem here is that unconstrained database access, to a key value store, to SQL database or whatever, makes it really hard for the runtime to automate operations, to automate things and make things really, really efficient. For example, it's impossible for the runtime or for the platform to know if the operation is a read or a write. Can it be cached? Can consistency be relaxed? Or is strong consistency always needed? Can it still operate under partitions and failures? If the runtime can understand the answers to these questions, he can make intelligent decisions a lot easier. But if it can't, then it's just looking at a black box. It can't do much. Examples. For example, if write operations are really fast and read operations are slow, you can add more memory to the database. That the database might be the bottleneck. If you're reading immutable values, it's always immutable. It won't never change. You can just safely add caching. No problem with that. You can do that on the fly even. If you detect that that's the case. If writes always must be serializable, then you can add sharding. Also that safely, single writers per entity, for example. And so there's a lot of things that the runtime can do if it's not a black box anymore. Okay, and I'll get back to that in a second. But in a sense, it's all about finding the right constraints because an open-ended world looks great, but it can actually be constraining in itself, because constraints can, in the reverse, be liberating. Just like Timothy Keller. Famously said that freedom is not so much the absence of restrictions as finding the right ones, the liberating restrictions. And I really believe that's what we need to do when it comes to managing state here in serverless. So just as function as a service is great of abstracting over communication, as I've said, message in and message out. The question I'm asking, we have asked ourselves, in the stateful version. Or addition, I'd rather say. We're not replacing anything, I want to say. We just want to add to what's already there. In a stateful addition, can we abstract over state the same way as we today abstract over communication? So instead of just having message in and message out, and the runtime, and the function doesn't need to care about where it came from and where it ends up, can I have just state in to the function and state out? It's sort of a simple idea, right? So this was what we've been looking into the last year, and what it would take to implement something like this. It's a lot more constrained world, but that opens up for liberating the runtime, the platform to do amazing things in terms of shuffling things around, optimizing reads, right? Caching, sharding, all the things that's hard. We just delegate that then. If we can live by this contract of state in, state out. Does that make sense? Are you with me? The thing is that CRUD doesn't necessarily fit this model because we can't just pass the entire data set in and out. CRUD in the sense of open-ended SQL, because it's just too liberated, too free. You can do too much. It's really hard to make these assumptions. So if not CRUD, or if not SQL, or open-ended queries, then what? I'll get back to that in a second. But first I just want to say that we have been working on this product, and it's called CloudState. So that's what this talk is about, as well as the ideas behind it. It's like more the ideas behind it, but I just want to say that we're actually implementing these out. It's not just a rant and some crazy ideas. They might be crazy, but they seem actually to work. So what is CloudState? Yeah. Short overview, it's open source, Apache 2. You can find it on cloudstate.io, by the way, on GitHub, also CloudState, github.com/cloudstate.io, if you want to go straight to the GitHub repo. The idea is that we should try to make, an addition to stateless, to serverless, function as a service, in order to make it stateful, So you actually can have those coexist. Certain parts of the application should still be stateless, absolutely. The more processing-centric side, for example. But certain parts of most non-trivial application needs to be stateful. So we try to add that to the picture here. It's a reference implementation, but it's also a specification and a protocol for it, because as you will see, we're implementing this through a protocol between client and server, which opens up for a lot of opportunities, I'll get back to. And so there can be more than one implementation of this, but we're focusing in on one. And then the idea is that let you focus even more on your business logic, and your data model and the workflow, and that's it. Don't have to care about all these other hard things of managing state at all, is the idea. So you shouldn't have to worry about managing the complexities of distributed concurrent systems. That's a given, right? You shouldn't have to worry about managing the distributed state. That means consistency, replication, and persistence of state. And you shouldn't need to worry about managing databases, service meshes, and all the other infrastructure. This is also classic serverless, but I'm just going to list it anyway. Managing message routing, scalability, failover recovery, and running and operating your applications. So it's all of what you get with classic functions as a service plus the state part. We're giving you that for managing state. And some of the technical highlights, how we go about and looking at this in the libraries we're using, is that first is polyglot, meaning that we have client libraries, in JavaScript, Java, and Go in the current repo that we have done, and it's actually being picked up greatly by the community. So we have very close to finished in some and early stages in others, but we have upcoming support from Python, .NET, Rust, Swift, and Scala, and your favorite language, if you want to help out. It's actually quite easy to do, because as I will get to why, and it's all thanks to this protocol. And it's also polystate. We have powerful state models. Different state models fit different use cases. Some are great for service record, long-term storage. Some other state models are great for just coordinating distributed state between components, for example, and everything in between. PolyDB, supporting SQL, NoSQL, NewSQL, and in-memory replication at this point as well. So it covers a lot of ground, and it does that by building on the foundation of Akka and Akka cluster, leveraging gRPC as the protocol. We're running on Knative and Kubernetes, and we're leveraging GraalVM. Since all this, I can just have to say that since all this is implemented in Java or Scala, it runs on the JVM. It can be problems for serverless because it takes a ton of time to boot up a JVM. This is where GraalVM comes in. If you don't know that, what that does is compile down the whole stack down to an image that you can run natively. So you go from seconds of startup time down to just almost instantly. Which means that that Java can compete well with Go and others in terms of startup time and memory consumption and these things, which is great. So Graal's good if you use it for the right, for what it's meant for. So just diving a little bit into the architecture so you can get this mental model of what it looks like or feels like. Sorry. So let's say you have 3 Kubernetes pods here. We're writing 3 user functions. They are sort of injected or running on each one of these Kubernetes pods. They can be written in any language that I talked about. One in Java, one in JavaScript, Go. They can be in different languages even, and coexisting using the same state model as well, which is also great, because you have different teams loving different languages. They can all communicate and working without having to thinking much, because state is abstracted away. Through this protocol and these data types. Okay, then we have this CloudState proxy. We sometimes call it proxy, sometimes call it sidecar, but it's this classic sidecar pattern that you have with Istio and Envoy and a lot of other things. It's quite popular pattern. So the idea is that if one user comes in and want to make a request to one of these functions now, it always goes through this proxy. And this proxy is managing the communication and the state on behalf of these functions. Okay, it speaks gRPC directly with the user function, and if we dive in a little bit closer here, you can see that actually the sidecar is running in the Kubernetes pod. It sits right next to the user function. You can see that the user function sits right next to the Akka sidecar or CloudState proxy. I'm going to call it Akka sidecar here. And what's interesting, here is where we start to leverage Akka and Akka cluster. I don't know if you're familiar with Akka. How many here have heard about Akka? You should. You're Swedish. It's an amazing mountain up in the northern part of Sweden. But it's also this. I was going to say brilliant, but I'm Swedish, so I should. It's a decent actor framework. Anyway, so you have all these sidecars forming an Akka cluster You know, and what that means, I'll get into details later. Okay. So let's say now a user want to call one of these. He might use HTTP, which is one of the supported protocols. You know, if you write a user function, we automatically generate HTTP endpoint, gRPC endpoint, and also you can use eventing like Google Pub Sub to communicate with it. So all this is generated for you. So this whole cluster collectively understands that okay, he want to talk to someone to function on this Kubernetes pod. So it redirects that to the sidecar in the Kubernetes pod that is relevant. The interesting thing is here, once the message ends up there, there's no more network hops. Because the sidecar sits right on the same Kubernetes pod as a user function is just using in IPC, like super fast, just local communication straight to the user function. And whoops, what am I doing? Okay, I don't know if it's a sign. Is it time's up? Anyway, the sidecar understands the communication and the potential state management, state in and state out. So if there is a change in state, it's starting to gossip that across all nodes to make sure that everyone knows who's holding what state. It can move state around, and rebalance the cluster, and even perhaps then move the function over if the cluster is rebalanced, just to make sure that the state is even distributed and then it's local to each function that's going to serve it. Okay. So all that is managing by Akka cluster. We might have one guy coming in with gRPC, which is also said one of the supported protocols, or eventing. We currently support Google Pub Sub. We are working on that, I'd say, but it's coming soon. So what can CloudState then help you with? Yeah, I have to say, with the disclaimer here that CloudState is meant to run as a service. Sure, you can download it from the GitHub repo and run it yourself, but then you need to manage, the Kubernetes, installation. You need to manage a cluster and all those things yourself. The idea is that, some vendor, whoever want to run it, or if it's a large company, you can set up an installation in-house, absolutely. But it's meant to be consumed from the programmer's perspective as a service, so you don't have to manage all of these things yourself. So someone needs to run this. That's the whole point of serverless, that you don't need to run it locally, or when you develop, and you don't need to run it. You can run it locally, of course, when you develop if it's beneficial, but you don't have to, and absolutely not in production. You should just push things up to the service. So if let's say we have this running as a managed service, then the benefits is pay as you go. On-demand instance creation, passivation, failover, auto scaling up and down is really zero ops. Automation on message routing and delivery, as I showed you, through this proxy. Automation of state management through this proxy. The only thing that functions is state in, state out, message in, message out. Okay. So how does it work then? I talked a little bit about this Akka cluster and Akka cluster management, and what is it really? Let's say you have all these sidecars, and they say they form an Akka cluster. They actually communicate more than these arrows in this circle, but they form this classic node ring. It's actually the same architecture that you have in Cassandra. I'm sure you're familiar with. Dynamo, it came actually from a paper called Dynamo, but that they based the research, of course, on Cord and these older sort of distributed node rings. But it's using gossiping, So it's using Akka, this actor. Every one of these is an actor. It's encapsulated state and behavior. It can move around. It's fully location transparent, and all these things. And they form this decentralized peer-to-peer model, where nodes can come and go, and the cluster just shrinks and grows. And if state is available, on all nodes, through cluster sharding and partitioning, it detects that, I need to start rebalancing and shuffle state around to make sure that it's evenly distributed. And all of these things are managed for you, and the routing is made, so I'll just show you just in a second instead of just talking about it. So now we also have all these user function sort of laid out on this in this node according to how the data resides in. So now let's say that you have one user coming in and he's querying some state. Or let's say you want to persist some state. Key is his entity key. It might be user ID or something like this. And he has some state, might be user session state or whatever, I don't know, or shopping cart in an iTeam, SKU, and something he put in the shopping cart. So Akka cluster now supports state sharding, set, and routing on entity key. So let's say that you know that it hits this top sidecar. That sidecar then say, okay, sorry, I don't have that. The function is not residing on my node, but I know where. You know, then it sort of forwards that request to the sidecar that has the function and the state running locally. Okay, and that can serve the user, you know, and the user can use that to communicate and persist things. Okay, so here it's important that we have this co-location of state and processing. So wherever you are in the cluster, you guarantee that the state is co-located with the processing. Okay. And it's also, of course, backed by this event log, or if you use like event sourcing, I will get into shortly, and but some sort of backend store to make this happen. And so, but the interesting thing is that it also supports this automatic failover and rehydration and rebalancing. So let's say that something fails here, you know, then the function is moved to some random node, and so a connection is restored, the cluster is healed. And it's then rehydrated back the state so it's fully available, fully ready to serve the next request. You know, so the next request that comes in, if it's a query in this case, can be served from this new replica running, you know, on this new Akka cluster node on this new Kubernetes pod. Are you with me? It's a little bit complicated, but I'll try to at least explain the basics. It also supports this, you know, this sort of gossiping. That's a sort of another side of it. It depends. This sort of cluster sharding and partitioning is great for durable, long-term durable state where you know is going to be there for quite some time. For coordination type of state, it's not the ideal though, because there's of course some effort to put state across the, you know, all this place, store it down in the back-end storage somewhere, and things like that. And then Akka clusters have you know what was sort of more efficient gossip replication. So let's say that we have gossip-based replication. Let's say we have one guy coming in and making an update to the shopping cart, but now it's implemented using these other techniques, you know, that I will get to in detail what that means. But the way it works is then, you know, that sort of the state is sort of ends up on one replica, but then sort of immediately automatically and transparently replicated to all other replicas. And you can set the replica depth, you know, if you want quorum or want to make sure that all replicas in your cluster gets it, and things like this. And you know, one classic, you know, data type that we'll get into is conflict-free replicated data types that fits this model very, very well. And here, you know, state is merged on the local node, and they can actually, and state can actually diverge, but it's guaranteed to always converge, you know. And it's extremely available, you know, because you can kill almost all nodes as long as there's a few alive that can still continue to gossip. When you add more nodes, then the new nodes will get updated. So you essentially need to kill the whole cluster in order to lose your data. That said, that could happen, so don't use it for long-term storage. More use it for coordination data, you know, and the type of session type state data, and things like this. It's also extremely scalable, of course. So I said that, you know, classic CRUD doesn't fit this model that well. So what models do fit? You know, some of the constrained, you know, yet battle-tested and really good models that we are using, and it's not limited to this. You know, anything that can fit this, you know, this protocol between client and server, abstracting the state models can fit, of course. So there might be other state models, but the ones we've implemented so far is event sourcing, CRDTs, you know, conflict-free replicated data types, and key value stores. So how many have heard about event sourcing, by the way? Almost everyone. You know, I don't know if I need to go through it that deeply, but for those that I'll just give you a refresher. So event sourcing, you know, fits the model of a system where you have events flowing around very, very well. For you have the concept is the high level concept is quite easy. You have the events flowing in the system, flowing into your service. since events are already flowing in the service, the question to be asked then, why not just store the events that lead to your state change rather than storing the actual state change? The events are already flowing, they're already in some queue, normally passing into your component. Why not just store that queue? Then you store, the effects, or the things that led to your state change more than storing the actual state change. And the interesting thing with this is that then you also store the history of what led up to why you have this state. Right? And that means that you have all history that's ever happened in your system. Instead, if you just store the state, you only have the snapshot of what it looks like right now. And that can be useful, but why not have both? Why not have the snapshot of what it looks like now inside your runtime component, and you have everything that ever led up to it on disk. So let's say you have a command coming in here, it ends up in this mailbox. Some sort of side effect happens that leads to a state change. Create an event out of that. Store it down into the event log. Just let the event pass through, essentially. Command turns into an event. Command, represents, I want to do something. An event represents, I did something. Store, I did something. Then you don't need to store the actual state that you have at this point. So this is the happy path. And the interesting thing is that then you can also have others subscribe to that event stream on the other side. To find out that there might be create shopping, add item to shopping cart, coming in, you're adding it, and then add item added to shopping cart. Others might find this guy added this item to shopping cart. The only thing he needs to do is subscribe to this event stream, and he finds out all that's going on to this in the shopping cart. And this is what Martin Fowler sometimes called a memory image, because it's really persisting the state in memory. Because it is as if the state is persisted in memory. It's as fast as in memory, but it's still durable on disk, but without the penalty of always going back and forth and fetching it. So it's really collocating state and processing very, very well here. Let's say that it fails now, okay? The nice thing is that it's extremely easy to recover from failure here. You simply just replay the events in the event log and bring the component up to where it was. So it fits this model of a fast recovery, an easy recovery, and this type of, really self-healing type of systems, that we built after with actor models very, very well. So now if a command comes in, the state is there. So some of the benefits of event sourcing, if we're just going to recap really, really fast. One single source of truth for all history. You don't need to have, the snapshot in one table and, you're making all, create a lot of tables for storing everything that happened, logging or auditing, as we usually call it. There's no need. You have one source of truth that contains everything that happened in the system and full auditing in one single event log. It's great. It allows for this, durable in-memory state. It avoids this, infamous object relational impedance mismatch because there is no mapping going on. You don't need to hibernate or, JPA and all of these things, because there's nothing to map. You use the state in your ideal format in your object, and you can still pay the benefits of being fully persisted without mapping. Others can subscribe to state changes I've talked about. It's also really good what Martin Thompson called mechanical sympathy. Essentially, that it fits modern hardware very, very well. So it's quite easy to implement in an efficient way. With single writer, just writing to disk in order, not just really this random access that you often have with other types of things. So the question is, serverless event sourcing, how does it work? Yeah, state in is the event log in. It's replayed when the component is activated after being passivated or when it comes back from failure. Okay, so it fits that very well. It's very easy. Just consume events after events. And your commands in and commands out, that's your messages. And the interface out is the events out, the events that I emit, that others can consume on their side. So you get this way of chaining these things very well with a well-defined protocol that fits this state model very well. Okay? Conflict-free replicated data types, they're a little bit harder to understand. I guess if you don't, how many have heard about them, by the way? Not that many. I'll just try to just briefly go through them. They stand for conflict-free replicated data types, CRDTs. And you know, there are a type of data types that have certain type of properties that fits very well, that works very well in distributed systems. You know, they are strong, but eventually consistent. They are guaranteed to always converge, even though they can diverge. They will guaranteed to always converge eventually. You know, and often if in a fast network, it's quite fast. You know, they are fully decentralized. As I said, you can add your nodes. You can just almost shrink down all nodes to one if it's live and kicking somewhere. You know, like a virus. As soon as others start coming, you know, just start spreading, you know, across the whole system again. You know, and so it's really cool. It's super highly available, super scalable, and it's sort of ongoing research, I have to say. Not all data types fit these properties because they need to be monotonically increasing. You know, that's the mathematical property of these, that knowledge always grows. And you can't remove knowledge. These data types, they have the same properties. You can only add knowledge. As soon as you start removing things, it gets complicated. Some of the data types, they allow removal, but you can't just say any data set should be a CRDT. You know, some of the ones that have been found and worked well and that we have implemented in Akka that we now make available to CloudState is counters, registers, sets, maps, and there are graphs as well. But I don't think we have them in Akka yet. You know, I can just skip this. You know, they are associate community wide and potent. Yeah, no one knows what that means anyway. Yeah, I'm just kidding. You should. So how does it fit this state model? You know, you have either the actual default state data type coming in. You know, that is known to converge very well, so they can all be done behind the scenes without user interaction. Or you have the deltas, because there are different types of CRDTs. Some are more efficiently implemented by just shipping the delta, the actual state change, but they can still be nicely converged behind the scenes. So you have the state coming in through this as a CRDT, and you have state deltas coming out. Again, this fits this model very well, being way more constrained, and make sure that the runtime can do all this magic behind the scenes. You just get an object, oh, here it is, you know, a fully updated, replicated shopping cart, just use it and then pass it on, you know, and the runtime takes care of the rest. So that's really, really nice. We also support CRUD. In the CRUD, I believe, so it actually do fit this model since it's so constrained. You have key value update, but I believe that's probably the least useful one because it still has update in place, which means that you don't have any history and all of those things. But a lot of people find it intuitive, and we support it. And since it, as I said, it doesn't have, you know, some of them have, you know, very advanced query languages, which makes it harder to support in this constrained model. But simple key value and get something on key, that fits this model quite well. Because you have, you know, snapshot in by entity key, and you have snapshot coming out, you know, updated. So that's also quite easy. So it fits this model well. So let's, is it 5 minutes left or something? Or, yeah. So I'm just going to give you a little glimpse of what it can look like. This, you know, it's fully available. You can just check out the GitHub repo and play with it yourself. I don't have time to run it here or anything, but I'll give you a glimpse of what it can look like. So let's say, what it does is that this little sample implements sort of one part of a chat app, you can say, or one part of any online apps. Where you want to track if a user is present somewhere in the cluster. You know, you might have cluster 100 nodes. All nodes should know if it's a user logged into any one of these nodes, and do this in a very efficient way. And also tracking, you know, if he's logged in more than once. He might be logged in with his mobile, and essentially tracking the presence. It's sort of a contrived example, but it sort of shows the building blocks quite well. So we start by writing this protobuf. That's the gRPC protocol, you know, and that defines the contract between your function that you write and the backend server doing all this magic. So here's first, you know, some just classic boilerplate. We don't need to care about that, but I'm having it for completeness. So here we define 3 different messages. First, we have user. And that's essentially just a wrapper around our entity key. You know, that's one key aspect that's important in CloudState. That we need to be able to define each function or each entity. by its key. So this CloudState.entity.key, that's a mandatory protobuf annotation, according to the protobuf spec, and if you add that there, we will generate a key for you. And then it has an online status message, just so you can subscribe to if the user is online, and it simply says yes or no, or it's a Boolean, yes or no. And then you have an empty message, when you don't need any response. And then here's the most interesting part. And this is the service API for our entity. It's not really function anymore, because functions should be stateless, but it's weird to talk about functions really. But I'm going to say entities here. So you have two methods here. Connect, which takes the user, essentially the entity key, so you can identify who I'm going to want to connect to. And here you get a stream of empties, because we don't really care about the response type. The second one, monitor, takes an entity key or the user, and you get an open stream of online statuses, so you can subscribe to changes in the cluster made to this user. Or to this data structure that keeps track of the user presence. So let's implement this entity then. First we create a regular Java class called the presence entity. We annotate it with CRDT entity, because here I'm going to use CRDTs because that fits perfectly for this type of use case. It shouldn't be long-term storage. It should just be awareness in the cluster if the user is available somewhere. If the whole cluster dies and it starts up, it's fine if I start from 0, because there will still not be any users. See what I'm saying? So here we have a specific data type that we have called vote. And vote can, of course, do more than just setting presence, but it works well for setting the actual presence here. So vote is a CRDT here that we provide from the framework. We have the username, that's our entity key. So each of these entities have one. And then you have the constructor. The main method is quite interesting, I think, because this is all it takes to actually kick this off. You create a new cloud state, you register your entity, omitted, essentially passing the class and the protobuf descriptor here, and then you kick it off by running start. That's all that's needed to kick this function off. But the business logic here is implemented in where we implement the service API. And we have two methods here, the connect and monitor. So in the connect method, we just create a regular Java method. We annotate it with command handler, which is like some of the plumbing that we need in the backbone of CloudState. It takes a stream command context. It's essentially saying that I have an option here opening a stream. And here, I'm simply saying, I want to update my CRDT here to say I'm available. So it sets this vote CRDT to true, and it doesn't need to do anything more. By doing that, it's automatically replicated across the whole cluster as needed. Others are merged, with this new state, and all that is taken care of for you. Okay. When it comes to the monitoring, I sort of omitted a little bit of the code here. There are some if statements and crap. You can take a look yourself. But that's why I just want to show the monitor. Here you actually have a chance of setting an on change on this context. It means that you can subscribe to changes to these CRDTs down on other nodes, by adding this lambda function or this on change. And then you can sort of pass that on to the by opening this stream. Now you can just pass that on to the user of this they can do just call this function for checking for online status. So I'm out of time. I just want to show you quickly how you do this with the final step with Kubernetes. Bear with me one minute. So you just install this. You install CloudState by essentially saying create namespace CloudState and apply CloudState and just download the YAML file, classic Kubernetes installation. You can install it our actual presence app by just applying this YAML for a presence function and for a gateway. And finally, in the last, I'm just showing you easily scale it up to 3 nodes, or you can just do it to 5, 10, 100 nodes. That's essentially all the necessary steps in order to run this little function in CloudState. So I'm a little bit over time, I'm sorry, but I just want to say, if you find this interesting, join us. We're looking for developers, users, ideas, rants, flames, or praise, or whatever. It's a fully open source project with a ton of contributors from many different communities. Go, Swift, Rust. Please join in. And take a look at CloudState.io and let me know what you think. So I'll be around the rest of the conference if you want to chat about this. Thank you.